Professor Swaminathan, good morning. Good morning, sir. How are you?
Hello, good morning, sir.
Hello, good morning. Good morning, sir.
Good morning, sir.
Good morning, everybody.
So, Prabhu sir, good morning. So, Prabhu.
Prabhu sir, good morning. Gurnule sir, good morning.
Good morning, sir.
Morning. Gurnule, good morning.
Bhagat sir, good morning.
Yes, sir. Very good morning.
Gurnule.
Yes, sir. Swaminathan sir, good morning.
Good morning.
Sir, very good morning, Swaminathan, sir. Damodar, sir.
எல்லாம் போட்டியாப்பா?
कुठे गेलं नाहीस ना? सकाळला गेलं अच्छा माहिती
Professor, good morning.
Yes, sir. Very good morning.
sir. Good morning. Hello.
Oh, sir.
Hello. Gurnule sir. Yes. नाही आता बरोबर आले आले हा हा या ठीक आहे ठीक.
Prabhu sir is okay now? Camera?
I'm okay. Can you
Okay, sir. Okay.
can hear me?
Rashmi madam?
Yes, sir.
Okay. We can start within 2 minutes. Okay?
Yes, sir. Yes.
Okay. प्रभू सर परेश सर नाही दिसत आहे.
दिसले नाही ते मी हाक पण मारली पण काय नाही आहे मला वाटतं ते.
हा बहुतेक हो.
You can start I think no problem.
एका मिनिटात सुरू करून देऊ आपण. ठीक आहे ना?
आरामात.
कमी इकडे हे
Okay.
Lisa, madam.
Uh,
Yes, sir.
हम लोग start कर दो. Start कर दो. ठीक है ना?
Okay.
Can we start now?
Yes, sir.
Rashmi madam, we can start now. Okay.
Lisa. Yes,
Okay.
sir.
Very good morning
Yeah, we are ready.
to all of you.
Okay, sir.
Sir, am I audible?
Yes, sir. I should start. Yeah. Okay. A very good morning to all dignitaries, guests, participants, and dear students. With great joy and immense excitation, today is beginning of Navratri, and it's our holy tradition
Madam, Rashmi madam, you are not audible.
Yes, sir. Yes, sir.
You are not audible. Start now. Your network is not good. Band. आपका वो नेटवर्क बराबर
Yes,
नहीं
sir,
है
I
बराबर
am
देख-
checking that.
हाँ यस यस
Okay, sir.
हाँ यस नाउ
A very good morning to all of you. I, Dr. Rashmee Dubey, first pay my homage to late Sri Govind Ravji Vanzari sir, founder, president of Amar Seva Mandal. It is my proud privilege to welcome Honorable Dr. Suhasini Vanjari ma'am, president of Amar Seva Mandal. Honorable Advocate Abhijit Ji Vanzari sir, secretary, Amar Seva Mandal. Honorable Dr. Smita Vanjari ma'am, treasurer, Amar Seva Mandal. Respected Professor D.V. Prabhu, General Secretary of ACT, Wilson College, Mumbai. Respected Dr. Brijesh Pare, President, ACT, Madhav Science Postgraduate College, Ujjain. Respected Dr. Rakhi Gupta, National Convener, Secretary, Central Zone, ACT, IIS, Jaipur. I also welcome respected Dr. Dilip Badvaik sir, Principal, Kamla Nehru Mahavidyalaya, Nagpur, and respected Dr. Pradeep Dhaikar sir, Vice Principal, Kamla Nehru Mahavidyalaya, Nagpur. I welcome convener of this national webinar, Dr. W.B. Gurnule, Secretary, West Zone, ACT, Kamla Nehru Mahavidyalaya, Nagpur, and co-convener, Professor M. Swaminathan, member, EC South Zone, ACT, Kalasalingam Academy of Research and Education, Krishna Koli, Tamil Nadu. I heartily welcome our eminent guest speaker, Honorable Professor PUNDLIK Bhagat, Department of Chemistry, School of Advanced Sciences, Vellore Institute of Technology, Vellore, and Honorable Dr. N. Sevapalam, Associate Professor, Center for Supramolecule Chemistry, Department of Chemistry, Kalasalingam University, Tamil Nadu. I heartily welcome all respected faculty members and all the participants from various colleges across India. Today, we are gathered here for second day of two-day national webinar on instrumental method of analysis, organized by Association of Chemistry Teachers in collaboration with Department of Chemistry, Kamla Nehru Mahavidyalaya, Nagpur, and Kalasalangam Academy of Research and Education, Krishna Koli, Tamil Nadu. On this auspicious occasion, we have a dynamic personality with us as a resource person, Dr. PUNDLIK Bhagat, Department of Chemistry, Vellore Institute of Technology, Vellore. Sir had completed his graduation and post-graduation from Sant Gadge Baba Amravati University, Amravati, and doctorate from the same university in the year 2005. Sir has more than 30 years of teaching experience and more than 20 years of research experience, starting from Jawahar Navodaya Vidyalaya, Osmanabad, Maharashtra. He also worked at J. Darda Institute of Engineering and Technology, Lohara, Yavatmal. And currently, he is working as a professor in Vellore Institute of Technology, Vellore. Sir had received Jawaharlal Nehru Centenary Award, being first merit of Amravati University, and also received Dr. APJ Abdul Kalam Advisory Award in FTRI 2019, organized by Vellore Institute of Technology. Sir has published more than 75 research papers and reports in various national and international journals and one patent. Sir had written 2 books. Under the guidance of Bhagat sir, 8 students has completed their research, and presently 6 are doing their PhD. So research projects which are completed by Sir are flowing and depository profiling of contaminants through domestic water supply system and health risks assessment by Tamil Nadu State Council for Science and Technology during the year 2011 to 2013. Similarly, synthesis of novel biomolecules, best ionic liquid and their metal complexes applications or biosensor fabrication SIR during the year 2015 to so invite respected Dr. PUNDLIK Bhagat enlighten us with his valuable knowledge on the topic optimum use of instrumentation to maximize resource output. Now, over to you, Bhagat sir.
Will you please allow me to share my screen?
Yes, sir.
Will you please allow me to share the screen? Yes.
Okay, sir. Yes.
Am I audible, sir?
Yes, sir. Yes, sir.
Screen is visible?
Yeah. It is visible, sir.
Is it okay now?
Yes.
Thank you, Professor Rashmee Madam. It is my privilege to stand at this online platform. First of all, I'm thankful to ACT who organized wonderful event to share some of the teaching and research experience. Particularly, I am most thankful to the college principal and other member like Secretary President of the Amar Seva Mandal, who has always supporting. Without their support, faculty and other staff member cannot organize any such event. Similarly, I would like to thank Professor Brijesh, who is the president of ACT. Similarly, other dignitaries, Professor Damodaram, Professor Swaminathan, and other dignitaries of ACT. I might not have mentioned all the names. Similarly, yesterday's I had a wonderful we have a wonderful series by Professor Dr. Sridhar from IICT Hyderabad, and Professor Uma. She has also delivered a fantastic, a lecture yesterday. Today, I would like to share some of my experiences. As yesterday, Uma Madam has explained that chemistry is a mother, really. Yes, chemistry, I can say it is a mother of all science subjects. So that is why, if we say mother, so there is no comparison in this world. Because we know mother only can take us to self-reliance. That what our present Prime Minister wants, that India should become self-reliance. But we need to do, as a chemistry teacher or as a chemistry researcher, as chemistry is a mother of all sciences. So few I have explained here, but this is not a limit. You will find any subject, any topic will be related somehow to the chemistry, and how chemistry will play a role in development of any institute, whether it is a government institute or private institute, or it is a research institute. So with respect to Wasudeo Gurnule, he has restricted me to discuss with other two topics, that is UV visible spectroscopy and IR spectroscopy. So I will try to reflect on this. Even though I had opportunity at my VAT, I'm working here since last 11 years. I got an opportunity to settle two instruments here, NMR and GCMS. I have opened from the box and made it available for the students. And really, NMR has become a wonderful for all of us, and that is why we are progressing. So here I will include very few application of the colorimetry as it is related to light. Then some examples I will comprising UV visible spectroscopy. Some few examples I will give how we can utilize our knowledge of IR and UV for developing our research. Of course, this is my experience. You can add something more, and you can inform to me through my mail also that I mentioned at the end. And how this is the last line which I mentioned here, how it is influencing research of the chemistry on overall ranking of the institute, any institute. That is why I'm talking. So here I have mentioned some of the spectroscopic technique which we are using. And here thermo-analytical techniques we are using. Depending on the research topic, we are using different techniques. Here atomic absorption spectroscopy is utilized for detection of the different elements depending on the type of the instrument we are using. Similarly, flame photometry also we can use in our research if it is available for detecting different element if we are working in either environmental or we are working in dye degradation and others. And ICP-AES, so this is more reliable, and it can give the concentration of the metal ion even in ppb level. Here some of the this diagram is indicating how different spectroscopic techniques are using, helping us. Molecular connectivity, NMR, Raman spectrometry is giving about orientation, IR is giving about chemical bond which are available and groups available, while UV visible is showing about reactivity and the absorption type of the molecule present, and X-ray yesterday sir has mentioned. So here I would like to concentrate only on UV and IR, so that is contributing and helping us to grow and compete the world. So spectroscopy is a branch, as I have touched to the some basics, as I know some of our research scholars are also there. So here it is an interaction of matter with light. So when we can say as an interaction of matter with the light is nothing but electromagnetic radiations which containing discrete photons. So these photons are nothing but oscillating electric and magnetic field, so which are perpendicular to each other. So this is beautiful the diagram which is explaining us. So how both of these fields are perpendicular to each other. So this is the relation which is showing of the energy relation, that I will skip it. So this diagram will be repeated in another slide also. So here these are UV and IR. So visible light, nowadays if you see the research with respect to photocatalysis, that now I have been shifted to photocatalysis in last 4 or 5 years. I will show you some of my the achievement done by my students. So UV and IR. So these three techniques we can use, that is the requirement of today's era. And particularly when we talk about UV, light, visible range. So we can have different types of color of the light corresponding to photon energy. So if you are interested in photocatalysis, so here UV visible spectrophotometer. So it will give a graph, or you can say a spectrum. So with respect to intensity of absorbed or emitted radiation versus frequency or wavelength. Here, when the light has been incident on the surface, so we know it will excite from ground level to ground state to excited state. That we can say HOMO to LUMO. So here it has been shown when the molecule interact with the light radiation. So electron will excite from ground state to excited state. I will go quickly with the next because it is very basic. Now when molecule absorbs electromagnetic radiation, so there may be three types of transition: electronic, vibrational, and rotational. When molecule absorb UV light, so it will excite, it will cause electronic transition, while IR radiation will contribute for vibration of the molecule, and microwave and for IR, so it will contribute rotational energy or rotation of the molecule. So here, so it has been shown the contribution of all the vibrations, rotation, and electronic transition. You will find here, it comparison is given. So it is a ratio, a maximum ratio you will find the electronic transition. So here it is given, if it is a photon of IR for IR and microwave is the absorbing, so it causes only rotation, while IR radiation, it will cause vibration as well as rotation. And if UV visible spectrum is absorbed, so it will cause all of this electronic transition along with vibration and rotational transition. That is why contribution is more here. So this I will skip, and it has shown, as it is already repeated. Now, as light has been absorbed, so there are two laws given by the Lambert and Beer. So here Lambert law related to intensity of the light will decrease with respect to length, while Beer has explained the intensity of the light is directly proportional to a decrease in intensity of light it depends on is proportional to the intensity of the incident light as well as concentration of the solution. While if you combine both of these, we can say here if concentration increases, absorption also increases, path length increases, absorbance also increases, and molar absorptivity will increase the absorbance. So likewise, this is a mathematical equation of Lambert and Beer law. This I will skip. So this also I will skip. So as we know, when UV or visible light is absorbed, it will cause any type of the transition. Maybe a sigma to sigma star, or you can say pi to pi star. If it is containing electron, it will cause the n to pi star or pi to pi star. So depending on the type of the molecule, whether it is containing single bond, double bond. So this slide is indicating which after absorption, which are the transition probability which are allowed. So if it is the epsilon coefficient is more than 10,000, then we can say it is allowed transition. Otherwise, it will be forbidden. So this is the term which is used in the UV visible spectroscopy. That is very important. So we can say chromophore is one of the very important. It is like a light like a baseball. It has been compared with different amount of the energy being thrown. So here we will find chromophore are part of the molecule that can catch this light radiation. It is very important, and it can catch photons with certain amount of energy. This is also very important, and it will help to excite the electron from one energy level to another energy level. And this wheel is showing the energy which is absorbed and corresponding light which is absorbed and light which is visible to us, because only visible radiations are being visible to us. So auxochrome is another a very important group which is playing a role. So this is maybe saturated or unsaturated, but do not absorb any specific color, but present along with the chromophore. So it will enhance the absorption. So it is like a room which is having the same light, but if we have a room with white color, so it will help to enhance the color. That is, intensity of light will be increases. So these are some of the groups given here. Shift or lower wavelength. So this is higher wavelength. Hyperchromic, it will increase the intensity, and hypochromic. So what are the changes taking place with respect to conjugation? For example, so here naphthalene is shown. So you will find then if it is one more conjugation has been increases, that is anthracene, and it is tetracene has been shown. So we'll find here the intensity of the light has been increased. As the conjugation is increasing, it will absorb in the more wavelength. That is, it is going towards the red shift, or we can say hypochromic shift. So here this CS2OH group, which is acting as a which is acting as an oxochrome. So if it is the removed by oxidation, then it will shift to hypochromic shift. So here this diagram is showing all the four concepts which I have explained here. So here it is going, if it is moving towards red shift, then it is bathochromic, and if it is moving towards blue shift, that is reducing wavelength. And hyperchromic, if it is going above, it means intensity increases, intensity decreases, it is called as hypo. So you will find this is the bentonite bond. If it is treated with alkali, ion. So the phenoxide ion will delocalize, and it will form a quinonate bond that is acting as a that is giving more conjugation. So it will move towards the red shift, or we can say, so it is absorbing towards a longer wavelength. Another example, so same example has been explained here, how it is forming, and you will find here the lambda max has been increased from 270 to 290. Now another beautiful example which you are always coming in contact with the phenolphthalein. So this, we know how color is changing, but there is a very big changes which are taking place the moment we are adding phenolphthalein. So it will convert to the pink color because of the conjugation which happened by abstraction of the proton with the help of strong alkali. This beautiful concept which is called as isobasic time point. So here you will find at different pH, sometimes molecule, particularly dye, they may give different lambda max at different pH. But at the same time, so they will intersect at the same point. So this point is called as isobasic point. So here also it is shown another example. So even though, so it will show different two lambda max here 535 and 880, but all are intersecting at this point. So this point is called as isobasic point. But main important thing is, see here at same absorbance, isobasic point at the same absorbance, it is given at the same concentration at different pH. So it means, so it is not pH dependent. Isobasic point, it is concentration dependent. So this is colorimetric, similar to UV visible. We can use for our some of our experiences. We can some of the simple experiment, like detection of nickel or detection of Fe2 plus or detection of copper. So that can be determined. Even small kinetics we can utilize by using some reactions. So colorimetry, this instrument is very, very simple and very it is very cheap also. So every college can keep this instrument so that our research scholar or our MSc student, they can utilize this. If we are changing one group to another group, and suppose product is color, so we can utilize this. We don't have UV visible, so we can use this colorimetry. It is a small instrument and can be handy. So this, the principle, it bends on the color which is absorbed. So the color which is observed by the naked eyes. So this principle I will skip because it is very well, it is studied by the students. So what are the requirement? We need colored compound. Of course, as I told you, if the reaction product is colored, or if reactant is colored and product is colorless, then we can take advantage of this. So this is the example I have shown. How we can go? So UV visible, as we know, these are all the textbook application I have shown. Very good applications, like extent of conjugation we can detect, identification of chromophore we can utilize, quantitative and qualitative analysis. At the end, I have mentioned here Hammett acidity. This is very important. We are using Hammett acidity of our heterogeneous catalysis. I will show you some of my 2-3 papers I included here. Beside this, we can use reaction kinetic. UV visible we can use for reaction kinetic and quantitative analysis by this method. For example, copper can be detected, Fe can be detected. We know very good blood red coloration is obtained. So our graduate student, they are doing this detection of the element. Even 12th standard student also, they are doing this copper and Fe. But we need to explore as a teacher to researcher, because everything is available, but we need to guide them just like mother is guiding child. So likewise, we need to make them. We should not allow them to cry that nothing is available. Even though nothing is available, whatever is available, that we should make them aware. They should utilize, and they can enhance, because while writing paper, and when paper goes to reviewer, we will not be there in front of him. So it should be self-explanatory, and reviewer should understand. Of course, this is my small experience in research. I may not have big experience. So reviewer should come to understand what the research scholar has done, or what author have done. So it should be self-speaking, just like we are expecting while checking the paper. So likewise, so this is application of this. Now I will move to IR spectroscopy. I will finish. I will another 20 minutes, so that last 10 minutes we can discuss. As I told you, IR spectroscopy, it is helping to the increase the vibration of the molecule. So here, this is some of the infrared radiations after absorption you will find. So it will absorb, some of the radiations will be transmitted, and the spectrum which is obtained, so that is called as a fingerprint of the sample. Why it is fingerprint? Because even a twin brothers or twin sister or twin brother and sister, say they will not have same fingerprint. So that is the beauty of the nature, how God has created like this. Every molecule will have the separate characteristic, the spectrum given by the IR. So that is the key we can utilize for detection of some of the groups, particularly groups. How we can convert, as I gave the example, we can convert, suppose acid to ester. So how much acid is present, or whether acid has been completely converted, so that can be detected with the help of this technique. So thus we can utilize to identify the unknown material. Of course, we need other techniques also, but suppose we don't have NMR or other techniques, at least we'll come to know, yes, my reaction is going on. Because we are helpless, because we don't have, I'm very sorry, even city like Nagpur and other part, so we don't have NMR facility. So I'll request, some of the member at the end we'll talk. So if these facilities are there, so how it is important, how VAT has grown with one instrument. And of course, we have all the instruments, but NMR has made a drastic changes in our research. So it can determine amount of the component in the mixture. So here you'll find. So I have mentioned here, no two compounds produce exact same infrared spectrum. So that is the beauty. Hence, we can use it for qualitative analysis. At least we can come to know whether particular expected compound is present or not. So there are 3 regions, as I mentioned here: near infra, mid infra, and far infra, and fingerprint region is also there. So this has been repeated, as now we are dealing with the molecular vibration, which is the caused by the IR radiations. So principle of the IR radiation, it depends on the Hooke law, which is explained with the help of the, suppose 2 atoms or 2 objects which are connected with spring. with having the which is having the force K. So it is the frequency of the molecule absorbed, frequency which is absorbed is directly dependent on this, the masses and the force constant. It is shown in the next slide. So here the frequency is directly proportional to force constant, that is bond strength, and inversely proportional to inversely proportional to masses. So here you will find stronger the bond, higher will be the stretching frequency, and larger the mass difference, so higher will be the stretching frequency. So here you will find these examples are showing. So CH bond is stronger than C deuterium and O and Cl. So here that is why stretching frequency is very high compared and decreasing towards CCl. Similarly, C triple bond, double bond and single bond, here stretching frequency is more compared to single bond. Now this diagram is showing how mass is influencing on the vibration. So lighter the molecule which is having 2 gram per mole mass, here 254 gram per mole iodine. So it is vibrating very fast compared to this. So it is very good example we can show it to students. Greater the mass, lower will be the wave number and frequency. So likewise, here infrared spectroscopy, which is connected to Hooke's law, we can explain with the help of this CC bond, double bond and triple bond. Here triple bond is having higher frequency. Similarly, so there is a beautiful example where the CH, which is connected here, the single bond, that is sp3, it is connected to sp2 environment. Here this is sp. So we can say in other words, if the S character is increasing, so frequency also increase. So here 29, 31 and 33 100 per centimeter. So here another example has been given. Heavier atoms attached, so frequency will decrease. So if heavier atoms are there, CH to CI, so frequency has been decreased. So here this model is showing how higher radiations are they generated, and so there are 3 different types of vibration possible: symmetric, asymmetric, then wagging, so these are twisting, scissoring, and rocking. So this is a very good model that can be shown to students to explain basic principle. So sometimes it is symmetric, it is shown, asymmetric, this is 2-dimensional model shown, and it is in the plane and out of the plane, and out of the plane, which is when the molecule is vibrating. So here this is showing how when the electromagnetic radiations are absorbed, particularly IR radiations, and after absorption, the vibration of the molecule is creating the spectrum. So this is the same diagram which is shown. So electromagnetic oscillating waves from the bond, which are reflected in the form of the coupled waves. So this instrumentation part I will skip. So which is containing the source, sample, monochromator, detector, and so this is, unless I include this may not be fulfilled. That is why just I included. We can see even there are beautiful videos are available, so student can understand these things. So primary use of this to detect functional group, and we can see we can identify the conversion of one molecule to other molecule, or we can see the change of conjugation, either by oxidation or reduction. For example, the fruits are ripened. When the fruits are ripened, the green color changes to yellow color. So there is a oxidation taking place. Now artificial ripening, we are adding ethene, so that ethene is acting as an oxidizing agent. It will oxidize, and it will form a chromophore there. So just like tomato is ripening, converting to red color. So these are some of the application given: identification and quantification of the organic molecule, analysis of powder are some of the examples given here. Of course, we can, I told you this IR spectroscopy will give an idea whether our compound has been formed. And the infrared, we need to confirm it by other techniques also. Infrared is used in the research for development, quality control, and quality assurance application. And Even it is used for the fiber. For example, maybe polyester or from acid to ester we are making. So these are some of the other I mentioned: pharmaceutical, forensic investigations, polymer analysis, lubricant formulation, fuel additives, food research. So this application I will skip. Now, what are the advantages and disadvantages? Among all the advantages, so like sensitivity, high wave number accuracy, resolution, sterilite wave number. So it is having major two disadvantages. It is very sensitive towards CO2 and H2O. So that is why instrument need to be free from both of this, as you will find many times we are using. So you will find a broad peak of CO2 as well as moisture. So here are some of the examples I would like to explain the application of this. There are, we can classify all the IR, the band in the 5 zones. So first zone is, OH, this is SP, CH, and this is NH. So OH, NH, and SP. So first zone is 3200 to 3700. So you will find when there is a broad peak, either it will be OH or it will be NH. And at the same time, SP, I told you, SP character, S character increases, so it will go to higher frequency. So these three you will get in the first zone. Second zone, so this is SP, this is SP2, either aryl or vinyl. Aryl or vinyl. So here it is in between 2700 to 32, is second zone. And so if just like table, our primary teacher is teaching to us. So like this, so it is very important for the research scholar. We can keep it on the table. Always we can see, and we can utilize this so that we will not confuse. So this is alkyl SP3 and aldehyde CH and carboxylic CH. So third zone is triple bond, and fifth zone is double bond. So this is triple bond C, triple bond N. Third zone, fifth zone will be double bond, and fourth zone is all aldehydes. So here you will find 1650 to 1850. So you will find 1850. So only anhydrides and acid chlorides are there, because acid chloride is influencing because of the high electronegativity, and anhydride it is having the CO, which is neighboring to again another O. And here you will find the ketone, aldehyde, and amide. Then you can remember it like this: acid and ester. So all the from the series we can say, so amide will be having the lowest, while ketone will be having the highest, but anhydride and acid chloride will be having the more the frequency. So fifth zone, as I told you, so third zone is triple bond, while fifth zone is double bond. So in addition to this, so this is another either C single bond or CO or CC or CN. So they are also absorbed around 1200. So this some of the examples I have given at the end. So what is given here also, as I told you, so we have to learn by the practice. So here, as we are saying, there are three different types of spectrum. Maybe strong peak, we are saying medium peak or weak peak. So if transmittation is low, or we can say if absorption is very high, then we are getting strong peak. If it is transmittance, more transmittance, then we will get medium peak. And if it is more transmittance, again, we are getting very, very weak peak. And we are getting broad peak sometimes because of the moisture content or because of the vibration of the molecules. So here, how it is related to, the dipole moment. So it has been shown. So I will show it here. So when the dipole moment is nothing but, bond dipole is nothing but the magnitude. It is the product of the charge separation and the length. So magnitude of the electronegativity difference and bond length. So if it is electronegativity increases, dipole moment will increase, bond length increases because both of these are increasing, dipole again increases. So bond dipole increases, absorption will increase. So we can say high polar bond is giving strong peak, and symmetrical, non-polar or nearly symmetrical, it will give weak peak, or sometimes it may be forbidden. So these are overall, the 5 bands which are shown here. So this first band, which is 30 to 37, and this is around 27 to 32. So CS stretch, and here triple bond, and this is double bond here. And around 1200, we are getting C single bond O, N, and CC. So I have shown some of the examples. I shall try to make you understand how we can give different examples. For example, as I told you, a bond strength will increase as a triple bond, double bond and single bond here. So it will be more as C triple bond C is having high strength. Similarly, isolated carbon-carbon double bond, it is having more compared to conjugated. So conjugation, so it will decrease. Conjugation, it will decrease the frequency. While aromatic carbon-carbon double bond, it is showing around 1600. So S character, this point has already been come, but it is, I'm repeating, stressing this point. So S character, if it is increasing, so here sp3, sp2, and sp. So it is having more. This is coming under first zone. So this is coming under second zone. And this is also coming under second zone. So here S character is 50%, where S character is 2/3. So likewise, and here another the beautiful example which is given, if the compound is aromatic and it is monosubstituted or disubstituted. So we can see here some of the overtone, or you can say repeated spectrum is obtained. So this overtone is because of the substitution present in the ring. So this is the example which is given. Some approximate values are given. Ortho, meta, and para substituted compounds are giving different absorption. So here some examples have been given. Another 10 minutes, I will finish up. So octane, which is having all carbon-carbon bond. So here, so you will find here carbon sp3 and sp2. So sp3 always showing to the right of the 3000. So here you see 3000 is here. It may not be possible to visible, but it is always to the right, and the sp2 will be to the left hand side. So here, so these are the medium, the peaks which are shown here. If it is containing double bond, so double bond means it is coming to the fifth zone. So here you will find fifth zone, which is coming under CC 1620 to 1680. So here it is shown. While again sp3, this will be sp3, which is coming just right hand side to this. So that can be identification of double bond. If triple bond is there, so triple bond, of course, so it is coming under the third zone. While double bond will come in the fifth zone. So here you will find, so this sp, which is the first, sorry, this carbon atom, carbon and hydrogen, which is coming in the first zone. So that is, it is shown here 32 to 3300 per centimeter, as it is having more more S character. Similarly, the other carbon atoms, carbon and hydrogen, they are just right hand side to the to this 3000, and this C triple bond C, so it is showing around 22, around 2000 to 2200. Similarly, aromatic CH is coming the second zone. So here you will find, so this is sp2 CH. So sp2 CH is coming the left hand side. See, this blue color is showing, this blue color is showing the left hand side of the 3000, while right hand side, so it will show the another CH. And here you will find the overtone which are obtained because of the presence of either monosubstituted or disubstituted compound. And this aromatic C double bond, so C double bond C, so they are coming under 1400 to 1600. Similarly, if it is ether, if it is diisopropyl ether, see CO bond is coming in this zone around 1200, while sp3CH is coming right hand side of the 3000. OH, of course, so it is a broad peak which is obtained, whether it is COH or OH only. So broad peak is obtained, which is coming under first zone. And so this is the same peak right hand side to the CH. And so the CO bond, which is coming around 1200. Similarly, so this is beautiful, instrument which is identifying primary, secondary, and tertiary amine. So oftenly we are performing Buchwald reaction. So Buchwald reaction may perform with either primary amine or secondary amine. So we can identify whether my primary amine has converted to alkyl secondary, or my secondary compound has been converted to tertiary. So that can be identified and given very good proof. So here NH2, it will give double peak, 2 peaks. Here this will be CH, and so another peak which is obtained here. So with respect to the CH around 1600. Similarly, say if it is again the single NH, or we can say secondary amine. So secondary amine is giving only single peak, while primary amine it is giving 2 peaks. Secondary amine is giving 1 peak. So it is the identification mark: primary, secondary, and tertiary. While tertiary amine is not giving any absorption here. So here this has been shown when we'll get sharp peak or when we'll get broad peak. So if there is a intermolecular hydrogen bonding, that I will show in the next slide. And here CH bond, so which is having the sharp peak, and CCH also will show the sharp peak. I will show the separate slide is there for to explain intermolecular hydrogen bonding. So this is another example where it containing CHO aldehyde. So this CHO aldehyde, it is showing the absorption. Of course, is carbonyl compound. Carbonyl carbon is showing the typical absorption around 1680 to 1730, and this is aliphatic, which is coming next to 3000. And you will find another doublet here because of the CH 2720 and 2820. So this is called as Fermi doublet. So this Fermi doublet is obtained because of the CH stretching. I will show here. See here again. So 2720 and 2820. So this is because of the combination of the CH stretching along with the CO. So this has been mentioned here. See, CH formyl stretching is in combination with CO. That is why we are getting doublet. So this is the very good tool for identification whether my aldehyde has been transferred to acid, or whether primary alcohol has been converted to aldehyde. Suppose we are doing oxidation. When I am doing control oxidation, when we are doing control oxidation, so whether aldehyde has formed or acid has formed, so that can be determined with the help of this. If we are getting this doublet, Fermi doublet, then we can say it is aldehyde. But if we are not getting Fermi doublet, it means it is acid. So this is identification tool. We need not wait, because see, we know the people those who are staying in Nagpur and nearby Vidarbha region, we don't have NMR. I don't think NMR is there since Mumbai. Only Mumbai and Pune you will find NCL and Mumbai IIT is there. But in between, till Bhubaneswar, we don't have NMR. So that is a very pathetic situation for the researcher. After sending sample, we need to wait for 2 months, 3 months. Sometimes it may take more time also. So by that time, we will forget it. But this will helpful for us because IR facility is available in Nagpur. So likewise, we can develop. Only we can develop when the students are there, and we can encourage students if they will encourage if the more facilities can be provided to them. So infrared spectrum of this ketone. So again, the CO and this CS3. So another example I can show here again, the same peak will come CO. I will skip this. And here you will find, so this acidic peak. So very, very broad peak. There is no Fermi doublet here. And the carboxylic acid, sometimes it will show dimer. Similarly, this is anhydride. So which is showing the peak above, CO bond is showing above 1800, as I shown. Similarly, propenyl chloride, CO again, COCl. So it will also show around 1800. And this one is amide, CONH2. So amide, as it is containing the NH2 group, it will show this the 2 peaks along with the amide, which is showing around 1600. Similarly, nitride, 2-nitropropane. So again, this is aliphatic region, and so this is CN bond, and the NO bond stretching is showing here. C triple bond, which is showing in the third region. So C triple bond C, so it will be showing the third region, that is 22 to 2400, and this will be sp3. Here you will find sometimes it is difficult to identify because both the compounds, you see, this is isopropyl alcohol and 2-butanol, so which is having almost same spectrum. So it will be difficult to identify, but we can do it. We can go ahead with this for the preliminary identification, and it can be confirmed further by the NMR. So here, why I was talking why broad peak and narrow peak is obtained, because of the intermolecular hydrogen bonding. If it is there, so it will lower or weaken the frequency of the bond. So here you will get the broad peak. So here, if the OH is free, then you will get sharp peak. While if it is participating in bond formation, then you will get broad peak. So this is representative spectra I have shown. If you convert, this is levulinic acid, which is a very good platform chemical obtained from biomass. Presently, we are working on biomass conversion. I have one patent also, what Dubey madam has said. So now this we have converted to suppose ester. So we can identify. So this is a broad peak and there is no peak here. So likewise, so one can identify without using any instruments like NMR. So we can sure that compound has been transformed. Here I would like to share some of my experiences. I moved from ionic liquid. Ionic liquid, of course, I am working with ionic liquid since I joined here, and I was not knowing what is, frankly speaking, I was not knowing what is impact factor. But VIT has given a very good platform to me to transform my thinking, and now I moved to of course I am growing now. Still now I am growing, so I could publish some good papers. I'm planning to go with some more good journals like green chemistry that already we are planning. So at present, as I told you, I'm working on photocatalysis. Very simple. So this is simple way to two representative pigments I have shown. One is phthalocyanine and other is porphyrin. So if you go with aldehyde and the pyrrole, so you will get this porphyrin, which is available in the natural photosynthetic catalyst, that is chlorophyll, and this phthalocyanine is available in many pigments. So both of these I have prepared. So this is here you will find. So this phthalocyanine we have taken as a precursor and we converted. Of course, I am a ionic liquid person. I am always incorporating some ionic liquid somewhere, because ionic liquid is helping to increase polarity in the reaction medium. And our catalyst, even the catalyst is heterogeneous, that is helping to catch the reactant and convert to product. It is beautiful. But initially, I was not sure that this compound will be heterogeneous. So one of the compound I converted to polymer, and this polymer compound I entangled here with the benzimidazole, and then finally again this second component I have prepared. So the first and second component both are containing cyanide. So here also cyanide. So I converted it into phthalocyanine by using DBU as a cyclizing agent, and further we converted to the epithalocyanine. So this epithalocyanine we utilize for dye degradation. So this I have shown that how we can utilize IR spectroscopy for identification changes which are taking place from reactant to product. And here UV visible spectroscopy I use for. So this is shown, that is called as DRS spectrum. So this diffuse reflectance spectroscopy is used to determine the band gap. So here the band gap is shown here. This is called as tau plot. And this particular photocatalyst I have utilized for methylene blue degradation, methyl violet, and Congo red. And so this can be identified with the help of. So this graph is shown which type of species are forming, intermediate species are forming. Like for example, holes are forming, electrons, these are the basic one. Beside this, it will form some radical, OH radical, superoxide radical. So that can be shown with the help of this. So this is representative diagram. And for your information, I am using homemade photocatalytic reactor. We have so many photocatalytic reactors, but everyone is busy. No one wants to share sometimes, because they will give primary importance to their group. So I found when one faculty said no to me, I welcome it. I did not say anything. Then I created a small photoreactor and I utilized the 5-watt light, even 5-watt simple LED light I use, and I got wonderful result. So this I will skip. There are the mechanism how it is taking place, and this is wonderfully. We have UPLC also at our center, TBI center. So this is one example I have shown. 10 ppm methylene blue we have taken, and before degradation we have shown after 20 minutes. So sorry, this is after 60 minutes. So you will find some peaks are there. This initial concentration, and this is after 20 minutes, 40 minutes, and 60 minutes. So you will find there is no original peak available in the sample. So this is the IR spectroscopy I utilize for testing recyclability of the catalyst. So this is before and after. So this paper has been published in Journal of Molecular Liquid. Similarly, here OH is there. I tried to prepare, again, polymer here, polymer supported one moiety, and this moiety I prepared without polymer, and both of them I combined with pyrrole. So of course, I'm getting here porphyrin. So this porphyrin with ionic liquid and COH group. So this is helping us with gene porphyrin. And this is again, I utilize for degradation of all azo compounds. So in previous, I utilized only one compound, but I got very good result. So that is why, so this is again scavenger studies which we perform to know which species are active during degradation. So this I will skip. And this is recyclability or reusability of the compound. Another 2-3 minutes I will take and finish. So this paper is published in Springer publisher. Then another compound, I got very good two papers, recent two papers. Again, pyrrole means I prepared is a very big moiety. So in the previous example, I prepared only one molecule, but here I prepared, instead of using polymer supported, I use this purlin as a base, which here this purlin is, it is acting as a electron supporter. So because when the light is incident, principle is when light is incident, so there is so many groups, sulfonic acid groups, they are having lone pair of electron. So this one of the electron will excited and it will reach to this place where it will react with the reactant and photocatalysis is taking place. So this I will skip. How this has been shown how the two reactants 1B, 1C and 2C, how it is a difference. So that can be shown as an additional characterization. And as I was explaining about Hammett acidity, the functional group which are present, sulfonic acid or COH group, that can be determined with the help of Hammett acidity. And UV visible is used again here. So this is DRS spectrum that is used for determination of band gap. So this catalyst I utilize for biomass conversion. We utilize peripheral alcohol to convert to ether. This octyl ether, and this we have blended with petrol, and we tested the characterization, combustion characterization. So here some more advanced I have utilized here. You will find peripheral alcohol, this OH group and ethanol OH group. So it is observed here up to 3 hours. So both of these, and after 9 hours you will not find any these peaks here. So it indicates, so both the groups have combined and there is formation of water molecule, and you will not find here this any one of the two. So it means the ether formation is taking place. So of course, if we have the facility, you can use it. Otherwise, it is difficult. And this is recyclability experiment. We have done it till 9 cycles. So these are the IR spectroscopy. 3rd cycle, 6th cycle, and 9th cycle. Till we get NMR, at least we can check it. If IR is available, in Nagpur it is available, I'm happy. So this paper wonderfully we publish. So it took 6 months to, so many times it came for revision, and we could, publish this wonderful paper. And this is another paper, phthalocyanine. I tried with, so my another group member has published this paper. So this is phthalocyanine base, again, same purlin moiety, but I have changed it to phthalocyanine instead of porphyrin. So this also we have utilized, again, same characterization UV, and this we have utilized for the biodiesel, preparation of biodiesel by using this homemade photocatalytic reactor. And here we have utilized, levulinic acid, which is a platform chemical. And this is recyclability, which is shown. And this is the change in the catalyst before and after 4th or 5th cycle. So this paper also I have published simultaneously. 2 papers I got, one from Vijay and other from Karan. Both are from the remote place I brought here. And this is the wonderful paper. Recently it has been published. It is an online. So this is wonderful achievement. You can also take it some part of this. Of course, I told you I am not expert in this, but this is the wonderful achievement by my group. That see how I have prepared this paraphenylene diamine I utilize, and this we have combined with aldehyde. So you can see my paper, this is available. And finally, we prepared photocatalyst. So that photocatalyst is again a very big, you will not be able to understand because it's very big, very, very big molecule. But see the wonderful, we tried this molecule. So by God's grace, we got NMR spectra also, H1 spectra also with negative, so the four protons here, 2 protons and these 2 protons are in the negative region, 4 firing region. So this is the biggest achievement of our group. And wonderfully, I'm telling you, Hake coupling or CC coupling is the heart of any industry, pharmaceutical industry or any chemical industry. And every scientist is trying to produce very good result without by forming green chemistry principle. Here in Hake coupling, we need to use either palladium catalyst, costlier catalyst, but without catalyst or without base. Please remember, without base, I performed this reaction and we got wonderful result. Not only Hake, even we got Sono-Glycera where we are using copper. Nothing is there, only catalyst, and that to 20 mg catalyst. So another reaction, Buchwald reaction also we could perform. So that also we got it. Ullmann reaction also. See, Ullmann reaction again we need tin. Nothing, no metal, no base, no metal. So again, this reaction, the same catalyst we are utilized for CH activation. So likewise, we have performed the recyclability, and so this is the diagram where this photocatalyst is used for different reactions. And this recently this paper has been accepted and it is available online. So this is the wonderful achievement. This is I published patent. I did not mention about this because some of the work is going on, and I'm happy that I'm getting a wonderful result with this. I could convert some of the biomass to energy. And see, I would like to show how VAT is growing and why VAT is growing. See, we have wonderful strength. 262 internal full-time teacher, internal full-time research scholar we have. Every research scholar is getting 20,000, even though they are away from the campus now. Recently they joined, but VAT has not deducted even single paisa, even from peon or to research scholar to director and dean. Everybody they paid money. This is the beauty of our management. And see, at the same time, mathematics also is not behind here. You will find total 732. We have physics, chemistry, and mathematics as a school of advanced sciences. And here I wanted to show you how chemistry can influence. We have the association of the teachers. I may be wrong. I'm very sorry. I may be wrong, but I'm saying any association, if suppose chemistry association is doing wonderful job by contributing something, if you collect 5,000 rupees, I will become a member and I will pay 5,000. If you pay 5,000, I will pay 10,000 rupees. And I request Brijesh Pare sir and other dignitaries members to start setting at least simple instruments to every college or at least center, at least district place. So that how chemistry, as I told you, chemistry, as madam also said, I am also saying, you also say, you may be, having greater experience than me. Of course, I'm growing, but I'm saying, so this is making a great influence. Chemistry is making a great influence because we call it as a mother. So you see, I wanted to highlight here age index of chemistry at present is 61. I will show you. See, citation is 5,884, 2020. Still some papers are coming out. So I will show you how it is growing. See, our chemistry is in QS ranking. Our chemistry is 450 to 500. Our chancellor is trying to, he is having dream to in next 5 years our VAT should be under 200 QS ranking. So within India we have 16th rank. And so this is a chemistry subject. We got 433, and so India ranking it is given. So our VAT is providing every year. VAT is giving some amount to us. Minimum 4 to 5 crore rupees VAT is given to us to chemistry department, or you can say SS department. And really, I can say it is a place to learn and chance to grow. I was a person from Amravati University, where the work is not. Industrial work is not carried out. I'm not saying it is, I'm thankful to my guide, Professor Damodar sir and my other groups. So here, so these are, I would like to highlight that VAT has been placed, in NIRF ranking under 15. And at the same time, so it is possible because of this, some of the highlights, I will skip this. I wanted to tell you that we have wonderful faculties Chemistry, we have 71 faculties in our campus. So now pandemic period, but last year 18,000 boys and 7,500 girls. Total 32,000 students are available in the campus. For your information, I'm telling, it is wonderful campus. You will not feel that you are in the India. You will feel that really it is a mini world, we can say. I will just finish it within 2 minutes. So this is possible because we have some centers, research centers that is helping us. This I want to say you. See, this is latest data, September 30. So VAT is always topping. We are trying to top in publication every month. Of course, we are focusing on quality now. See, SAS, School of Advanced Sciences, is always leading. So you will find this is monthly journal every month, and every paper for information. I'm telling you, management is giving research scholar. Every first author who is there, he is getting 10,000 rupees for first paper. Second paper 15,000. Third paper, fourth paper onwards, he is getting 20,000 per 30,000 rupees per paper. So if student is publishing paper, so he will be enhanced by this award. See, I wanted to show you how H index of the VAT is 109. When I joined 2009, H index was just 56. Now it has doubled, 109. But you see how it is influencing. See the H index of the chemistry. As a teacher, as a researcher, you can see, you should be proud how chemistry can be a magic player in the development of the institute. And I found in the engineering colleges and other colleges, any institute who is giving importance to basic sciences, then only institute can grow. Even you go to Harvard or Oxford, any other big institutes like IITs and any other renowned institute to go, chemistry and other sciences are given 100% importance. And we are following IIT pattern or Oxford pattern, that even chemistry person can work in electronic department or electronic. Some of the students are working with our faculty members. So this we need to follow. So here this I shown how chemistry has been grown from 15 to 14, 2020. And again, VAT has been announced as a Institute of Eminence among the 10. So this is possible by teaching, research, and employability. So this I will skip. So we have the courses. So we have so much of instruments except single crystal XRD. That single crystal XRD also it is coming this year. And recently HRMS has been installed, and it is about to start for services to students. So these are some of the research areas, and these are my some of the proud research scholars. Recently he has passed. So this Avinash is working in Zydus Cadila. Before completing PhD, he got job in Zydus Cadila in Gujarat. So he is a professor, Prashant. He is assistant professor in Yautmal, Amalaksham College. And these are my groups. And this presently all my fellow workers working with me. So both of them are from very small village. And this fellow is also from small village. He is from Buldana district. So this fellow from Amravati. This is from proper Amravati, and these two people are from Kolhapur. So of course I am very sorry if you say all are from Maharashtra. Yes, I am taking from Maharashtra because I want to grow with them, because they are not getting facilities. And this time I found in January we conducted one conference. So he is a scientist at LICAD, Germany. He is my very good friend, and this is my group. He is S. Senthil Kumar and his wife. So they are very good researcher. And when I joined with them, I was not knowing what is impact, but he has helped me to grow along with my students. And this is the award what madam has told. VAT is encouraging, and these are some of the glimpses. We are celebrating birthday of our chancellor is now 85, but you will not find he is very active person, and we are carrying out every district, 36 districts of Tamil Nadu. VAT is giving chance to one boy and one girl topper. Free education, 100% free. Lodging, boarding, everything is free. So VAT is adopting such students every year, and along with this, VAT is encouraging to have some clubs. So we have literary club, Marathi literary club. I am a faculty in charge, and these are the students, normally third year students. All they are taking care. And this is Gudi Padwa. We are celebrating. They are giving freedom to everyone. And this is a group, very beautiful group of my all students. Last year, because of some country, we could not conduct this program. Mrinal Kulkarni, she has accepted last time. It was on 21st March. But before week itself, pandemic has situation started, and we missed the opportunity. But I hope I can end with this. Successful people have two things: silence and smile. So smile is for resolving the problem, and silence is to avoid the problem. So very important. Please correct me. I'm a small person, and I'm always welcome with your suggestion. You can write to me, and you are welcome. If you come any time near Tirupati or near Chennai, you just call me, and I will give my number to you. It is with Gurnule sir. Anybody, any research scholar, anybody, please come. I am welcoming, and I'm thankful to all members, those who have given me opportunity to share my experiences. Thank you so much.
Thank you, sir. Thank you so much, sir, for your valuable and very informative session. So many students and participants thanking you for your effective and informative session. And sir, really, we need NMR in the Nagpur region. We really need it. So thank you so much.
I request you,
Here,
will you please allow me to, just 1 minute. I will request Brijesh Pare once again and Professor Damodar and Swaminathan sir to take initiative to provide at least one NMR. We have NIRI in Nagpur. We have
Yes,
NIRI in
sir.
Nagpur, Cotton Research Center in Nagpur. But I am very sorry,
Yes, sir.
we don't have NMR facility. If you give NMR, I will come there to guide you. Of course, I am not expert, but NMR and GCMS, 11 months I took pen to commission this NMR. I can help you. Please go ahead,
Yes,
madam.
sir. Yes, sir. Thank you, sir. Here I am sharing. We are sharing here with mail ID of sir with all the participants, so that you will be able to mail him also for asking your questions. Now it is the time to move towards the
Rashmee.
question answer session.
Rashmee,
And
two questions are there.
Yes, sir.
Hello.
Yes, sir,
Sir,
please.
some students have given some questions in the chat box.
Yes,
Sure,
sir.
please.
First question is from Sonia Verandani.
Yes, sir.
Explain how FTIR is useful for identification of inorganic compound.
Inorganic compound, it may not be feasible, but if it is having some, as it is, IR is related to functional groups, detection of functional group, or carbon-carbon double bond, single bond, and oxochrome chromophore. So I don't think it is useful. But if it is, suppose if you go to nowadays we are working hybrid catalyst. Like if you combine some inorganic compound, for example, we are preparing nanoparticle, Ap2O3 or zinc oxide nanoparticle along with some COH group. So that is helpful. COH group is there, or a sulfonic acid group is there. So these groups can be detected with the help of IR. Thank you.
Okay, a second question is also there.
Again, one question is here from Yamini Sahu. What are the ways for infrared thermograph to measure the exact temperature of a surface without contact?
Can you repeat, madam, question?
What are the ways for infrared thermograph to measure the exact temperature of a surface without contact?
No, I think I don't know this question. I will.
So I'm repeating question again.
Ask the student,
Sir,
to write
I'm
to me.
repeating the question. What
Yes,
are
sir.
the ways, except for infrared thermography, to measure the exact temperature of a surface without contact?
Yes, sir. I will search and give the
Okay,
answer.
sir.
You ask student to write to me. I will give.
Yes. I mean, it's so.
100% I will give.
One more question is that what is the reference book for IR spectroscopy?
IR spectroscopy at present, Sharma, Verma Sharma is a very good book, for basic learning. I suggest our student to go with Indian author first, any Indian author first, and then you can go with foreign author book. And for students' information, IR spectra of the each compound is available in NIST library, so they can check. They can find out whether spectra which is obtained of our compound is matching with the spectra of the other compound. All spectra are available in the NIST library that can be available. Thank you.
Thank you, sir.
Yes, madam.
Now, proceeding further towards our next speaker for today's technical session, Dr. N. Sevapallam, Associate Professor, Center for Supramolecular Chemistry, Department of Chemistry, Kalasilingam University, Tamil Nadu. Currently, Sir is working as an Associate Professor at Center for Supramolecular Chemistry,
Come here.
International Research Center and Department of Chemistry, Kalasilingam University, Tamil Nadu. Sir has completed BSc in Chemistry from Madurai Kamraj University, Madurai in 1985 and MSc from Mysore University, Mysore in 1990. Sir had done PhD from Indian Institute of Technology, Delhi. Sir has vast experience in research and teaching in India as well as abroad. Sir had worked as biophysicist at Cancer Institute, Adyar, Chennai. He also worked as research associate at Indian Institute of Science, Bangalore, and had experience as postdoc researcher in Korea, Advan Institute of Science and Technology, Daejeon, South Korea. Sir has also worked as a research professor in Postech, Pohang, and South Korea. Sir has total 55 publications in various national and international conferences and journals. Sir has 23 patents and written a book named as International Book on Curbiticules. So his area of interest are organic synthesis, supramolecular chemistry, and surfactants, fluorescence sensors, graphene oxide based sensor, and many more. So we have a person with knowledge and skill, and I invite Dr. N. Sevapallam sir for this technical session to throw light on the topic application of NMR in supramolecular chemistry. Now it is over to you, sir.
Yes, madam. Thank you. Please allow me to share the screen for the Narayanan Selvapallam.
Yes, sir.
So you can share now.
Yes, sir. Yes. Sir, is it audible?
Yes, sir.
Yes, yes.
Yes, sir. Thank you, sir.
Okay, yeah.
So thank you, Madam Rashmee Dubey, for a wonderful introduction. I also like to thank Professor Swaminathan for helping to participate in this webinar series. So I basically, my name is Selvapallam. I spent quite a number of years in abroad to learn many techniques. When Professor Swaminathan asked me to represent some instrumentation methods of analysis, I was really wondering what kind of a topic which I can share to the students and to the faculties. Then suddenly he said, okay, why not about the NMR? Okay, they accepted. Okay. But the NMR is something, we had been spending a quite number of years with the NMR. So it's very easy to every one of you to understand what NMR can do. But usually the NMR until now has been used for the purpose of characterization of organic molecule. Okay, that everyone knows that. And NMR has been grown up from the 60 megahertz NMR to now it's 900 megahertz NMR is available. Okay, so now it has even come to the desktop NMR. So NMR area is quite fascinatingly growing fast. Okay, so it's very interesting. But at the same time, supramolecular chemistry also contribute a lot to the NMR area of research. Okay, so that is what we are going to see here. Okay, so normally you characterize the compounds by the NMR, particularly as I told you, only the organic molecules. But in supramolecular chemistry, the molecules can be captured inside the cavity. Then they behave totally different. That's what we are going to see here. So this is the NMR machine that while in abroad, we are free to use NMR. As Professor Bhagat said, having the NMR is so wonderful in his hand. But in abroad, this is freely we can use anytime, 24 hours, it's freely available. And we are free to operate NMR by ourselves. Okay, I wish at some point of India also will get such an opportunity for every one of the scholars. There are scholars, BSc students, MSc students, all the students, they freely use the NMR. Okay, I hope such a state will come to India also within 10 years of time under the Modi government. I hope so. So this is the NMR machine. I think this is maybe around 500 megahertz NMR. So on the top, we can load the NMR tubes. And this is a big magnet. This magnet has to be maintained by the liquid nitrogen. Okay, so every now and then, we have to fill up the liquid nitrogen to maintain the magnetic property of the supermagnet of the NMR machine. Okay, so systematically it has to be maintained, and some problem will come always when we work with this NMR. We always get some problem, and there will be one technician will be there always available. Okay, he will immediately help us to solve the problem. Okay, that is the kind of situation. So this is the desktop NMR. I think this is one of the easiest and the cheapest NMR machine. It's available in India also. The cost of this machine is around, I think around 30 lakhs to 40 lakhs. I tried to get this one by the DST project, but unfortunately, they did not sanction this machine for me. Okay, so this is a kind of a condition in India. Okay, so this is the very smallest NMR machine, and this is another small NMR machine which you can keep it at desktop. Okay, so you can conveniently use to do some kind of studies, at least basic studies. So as I mentioned to you, when I entered into IIT Delhi, when I was doing the PhD, we had only around 100 megahertz NMR, and in Bombay, IIT they had a 60 megahertz NMR. Okay, so we used to get the NMRs by this kind of machines, and the resolution is always very poor and very difficult to get a very standard NMR out of that. And it in 1970s, as you see the graph. So in 60s and 70s, we had only 60 to 80 megahertz NMR. Okay, and over the period of time, it has grown up in such a way that nowadays we can easily get 900 megahertz NMR. Even now, my professor in Korea is having a 800 megahertz NMR independently for his group. Okay, so imagine like such a kind of condition what we are having it in India. Okay, I hope, as I mentioned to you, over a period of time, surely we'll also grow up like that. As Professor Bhagat shown very well, how India is growing fast, and particularly VIT and private universities such as VIT, Kalasalingam University, they are contributing a lot to the growth of chemistry. And chemistry is all about the mother of all the subjects. Without chemistry, no discipline in any of the engineering discipline can survive. So even they are always collaborate with us. Okay, that's a great moment for us. So learning chemistry and understanding chemistry is more important. That's what exactly Dr. Bhagat mentioned about in his presentation. How do you understand? How do you understand the molecular level chemistry? See, this is all about the entire science. Because molecule, we cannot see our naked eye. We cannot see. Surely we cannot see. That is why all these instruments such as UV visible, and all other instrument has come into the point. Okay. I think my internet is problem. Yeah. Okay. So, so that is the kind of situation. So we have to so we have to understand everything in a molecular level. There are the differences. So there are few scientists, those who are working as a professor right now, or those who are working in industries, they have understood the molecular level chemistry of this particular subject. Okay. So there are the differences. Just simply studying chemistry, organic chemistry, inorganic chemistry, or whatever the chemistry you are getting expert. But only thing is that how much you understood, how much you can understand the basic of all these molecular level developments. They're the differences. Okay. So for that purpose only, all this instrument has come into the picture. Okay. So all these instruments basically try to help you to understand the molecular level transformation. So like we are most of the time, we are utilizing the electromagnetic radiation to interact with a molecule. So that will give some information that from that we can understand what level it is, what kind of molecule it is, what kind of a shape it is, what kind of a orientation it is, and what it can do for us. Okay. So all these things. So today is a Sunday. I'm in the home, so my internet is not that stable. Sorry. So the electromagnetic radiation. Hello. So the electromagnetic radiation. Hello.
Hello. Sir, share your screen.
Hello.
Sir. Share your screen, sir. Hello. Sir, okay.
Yes, sir. Sorry. My internet is today because in the home I don't get a good internet. Usually I go to the office. So the electromagnetic radiation, which plays a major role. Okay. So even in the NMR also, we are using the radio frequency to interact with the molecules. Okay. So the molecules are under the heavy magnetic force, and then the orientation, by the orientation of the spinning of the electrons, we could able to understand what kind of molecule it is. So this is some of the basic discoveries based on that one. Hello.
Yes, sir.
Okay, sir. Now.
Yes, sir. Sorry, sir.
Okay. Okay. Yeah.
Today.
Okay.
Yes, sir. So the electromagnetic radiation, that is what exactly the previous speaker also mentioned about that. So the electromagnetic radiation through which we could able to interact with the molecule. Okay. Through that we can understand the molecular level connection. Okay. So Einstein, his discovery and his theories made a lot of difference in the science. Okay. So basically the NMR, as they shown here that, so most of the time, whether it is the extracrystallography, whether the UV spectroscopy, or FTIR, or any other kind of instrument, most of the cases, we are making the molecule to interact with electromagnetic radiation, and then the response basically helps us to understand the level of molecule. So this is about the UV visible spectroscopy. And in the case of NMR, it's a very peculiar thing because here we are allowing the electron to spin. Usually we know that electron can spin in the different ways. Okay, and when they spin it, they also behave like a small magnet. Okay, they also have some small magnetic force, but those electrons of the molecules, when they are located under the heavy magnetic force, then they are different. They are mostly function as a different kind of a material. Okay, so that is what we are going to see here. So under the magnetic field, okay, when they are in the no field, as you see here, see when they are not in the magnetic field, they are freely to rotate anywhere, and they can spin it in any direction which they like it. Okay, it's like a or a top mark. Okay, it's like a top. It can spin like any kind of a location, any kind of a direction like that. But when it is under the magnetic field, they have to orient in a particular direction. That is what exactly help us to understand what kind of molecule it is. Okay, so there are so many like elements such as hydrogen NMR, carbon 13 NMR, nitrogen NMR, and fluorine NMR, phosphorus 13 NMR, and there are many more. It's still on the way. So this is the kind of how the molecule is experiencing the magnetic force, external force, and what is the magnetic force of the particular atom in a particular molecule. That makes the difference. Okay, That is what exactly giving the chemical shift of the particular molecule. So here is again that how they are, differing by the experiencing the magnetic field of a particular atom in a molecule. So this is all a lot of theories behind that one. So this is the gyro magnetic force, and we are measuring by basically the RF factor of the particular element. And here is showing that how the frequency of radiation is absorbed. And as I mentioned to you, they release the energy in the form of a radio frequency. Okay, so they match the radio frequency when they are having the under the magnetic force. Okay, from that we can understand how much of the energy is required to match with the spinning energy of the particular element in a molecule. Sorry? Yes, so these are some of the fundamentals. I'll just go through that. Okay, so as a, for example, simple like NMR spectrum, you can see that there are a lot of peaks over that, right? So all these, peaks are basically represent what kind of a hydrogen is present in what kind of atom it is. Okay, so it tells us about, as you see here, multiplicity. We can also get the integral to quantify the number of hydrogen, and we can get the chemical shift to understand what kind of a functional group is that one. And overall, we can see kind of, many information from a simple NMR. Okay. So we can get basically help us to understand the spectrum overall. Okay. Based on the nuclear spin of a particular magnetic force. Okay. So here again, the magnetic field and their, chemical environment, and how much it has been getting the shield, and how the electron density is over there, and how the functional groups are there, and what type of hybridization is there. So all this information is contribute toward the chemical shift of the particular element. Okay. For example, like hydrogen. Okay. Hydrogen NMR. So that hydrogen NMR, if you take the NMR of that one, it basically tells us what kind of a chemical environment it exposed, and what kind of a shielding effect is there in a particular proton. Okay, so all this information, whatever given here, can help us to understand about the molecular nature of particular substance. So again, this is the same information. So in overall, we can understand about the hydrogen bonding and electron density and all those information, even electronegativity, all those things. Okay, so this is all, I think, good enough to understand what the NMR can do for us. Okay. I hope most of us about what the NMR is, so I don't want to spend more time on that. So one thing I want to stress is that when I was, started doing a PhD in IIT Delhi, I was really wondering what this NMR can help us. Okay. At the time, one thing which I learned that electronegativity of the particular atom really makes a large difference. Okay. So whenever there is a electronegative atom, suppose if it's a very strong electronegative atom, then usually the chemical shift is increase a lot. Okay. So that is the one thing which I understood. From that, I could able to easily understand the NMR of any of the molecule which I researched on that time. So the electronegativity is one of the major factor which plays for the chemical shift. And of course, amide bond, alcohol, whatever be the functional group, you can easily understand from that. So this is the general graph representation to show you that what hydrogen and how the chemical shift will affected by the particular functional group. So this is the only graph which helped us to understand what kind of compound it is in a basic level. Okay. For example, whenever I want to look for the CH3 or kind of having no functional group at all. Okay. They always appear between 1 to 0. Okay. Even sometimes after the column chromatography, I used to get this some peaks between 1 to 0 because there we used petroleum ether, and from the petroleum ether we get some hydrocarbons. So those hydrocarbons always appear between 1 to 0. Okay. Similarly, like any kind of ketone, particularly like acetone. Whenever I use acetone as a solvent, I always find it between the 2. Okay. Even for example, like DM as a solvent, I can find the peak 2.5. Okay. And whenever I look for alcohol, I always look around 3 to 4. Okay. And even if there is a substitution like bromo, chloro, usually I find it between 3 to 4. I look for that place, whether I can get any peak at the location or not. But whenever there's a OH or NH, then even though it is proton is there, but we cannot find them easily. Okay. Unless if the solvent is like a chloroform. If it is a chloroform, it's quite easy to see that. Okay. But if you use a DMSO, then it's very difficult to find the OH peak or NH peak. Okay. It's very hard. Okay. Similarly, like when there's a double bond, I always see between the 5 to 6. Okay. Whenever there's aromatic, I always look between 7 to 8. Okay. And whenever my compound having the aldehyde group, I immediately see whether I get any peak between 9 to 10. Okay. And carboxylic acid, it is also same problem. It's not easy to find it. Okay. But sometimes a small peak appears around 11 point something. Okay. So this is how I learned NMR. And this is the very much fundamental. And now the current generation, most of them, whether they are graduated from the normal college or from the somewhat reputed universities, I find they are finding difficult to understand and predict the NMR. They just go through the ChemDraw and just they draw the ChemDraw file and they compare the product. This is the kind of the generation what we have. They should change. Okay. So understand the basics of the NMR. Then you analyze your NMR accordingly. The software is just meant to help you. That is not the final. You understand? So there are a lot of things behind the shielding effect. So this is all because of the shielding effect. See, when there is a, like for example, aldehyde. The aldehyde, this hydrogen is under the force of carbonyl. Then how it can give you, peaks between 1 to 0? It naturally, it's highly acidic hydrogen. So it cannot give in the same environment as the simple hydrocarbon. Okay. That is how you have to see that. Okay. This is again the, similar information. So like, electronegativity. This is what I learned, as I told you. Electronegativity plays a major role to understand the chemical shift of the compound. So don't trust the, software and, look for the compound according to that one. So this is a simple, another NMR. This is ethanol. Okay. So ethanol, when I look at the NMR, it always puzzling me because it always give a, for this I get a quartet, and for the, for this CH3, I get always, a triplet. Okay. So this is, kind of multiplicity. The multiplicity usually help us to understand how many hydrogens are there in a particular carbon. That's why, that's the only way you can find out that. So, as I mentioned to you, instead of, depend on the software, better you predict yourself, the NMR spectra. From that only, you can understand the molecular level of all these molecules. Okay. So that is what I want to say. Okay. All the research scholars, please don't trust on the software such as ChemDraw to understand the chemical spectrum or the compound that you synthesize, but rather than understand the fundamental level of the molecule through the NMR spectrum. Then you try to see that. What is the difference? Even a small peak, a small shift, give a lot of information to you. Okay. If there's a hydrogen bonding, naturally it will shift in a different location. Okay. So that is how you have to see the molecule. Okay. So where it can be applied? That's another question. So NMR can be applied, many different locations. And as you see here, it can be, used in the protein, hydration, and, material science, and the molecular level dynamics, and also chemical analysis. And the protein folding is another thing. And so it's been wonderfully used in every application. It's very difficult to name where it cannot be, used of. Okay, now I'll come to my own research area. So we have been working on the wonderful molecule. I cannot say molecule. This can be a kind of, supramolecular material, host material. We call a host. The host meaning is that, suppose when some guests come, our form is a host. I'm the host. Okay, that means I can accommodate the guest in my home. So here also the same thing. It will accommodate the guest molecule non-covalently. That's the most important point. Non-covalently means there is no bonding at all. Only a very feeble interaction, and that is a dynamic. Most of our biological system, even like our breathing, it's working by the supramolecular nature only. Our hemoglobin is being accepted the oxygen molecule, and the oxygen molecule will be delivered to the cell, and then again it will get back. The hemoglobin will get back the carbon dioxide, and then deliver back into our this one lungs. Okay, so that we can get the breathing, getting the oxygen, and then going back and coming back to accommodate the next set of oxygen molecule. This is the host gas system. So biology is functioning entirely by this host gas system. That means you understand that how important to study about the host gas system so that we could able to manipulate our biological system. Okay, in that way, supramolecular chemistry really playing a major role in every aspect of our life. Okay, although their applications are until now it's a very limited, but I'm sure at some point this application of supramolecular chemistry is going to be very much in a better way. Okay, so this is a molecule we called as a cucurbiturial, and the left hand side is the one cyclodextrin, beta cyclodextrin. The wonderful of nature of these two molecules is that they are water soluble, and most of the biological system are working on by the water solubility. So our body has, more than 70% of our body is made by the water. Okay, so here we want to see that how the spin of the nuclei, in a particular hydrogen, and how they are going to function, and how this spin of the nuclei is going to support the NMR. Okay, so this is the kind of molecule. This is not a molecule. It's kind of a polymeric nature. So that is a cucurbiturial. Okay, so this cucurbiturial having a cavity. Wonderfully, they have a cavity, and it's a water soluble. It can accommodate the molecule inside the host system. Okay, and similarly cyclodextrin. This is also water soluble. They can accommodate any kind of molecule. Okay, we will see what kind of molecule it can hold. So this is a simple example. For example, in cucurbiturial 7, if we put the acetylcholine, choline. So if you put the choline here, see the molecular representation here. So it is originally like locating at a different place, the proton NMR of the starting material. See if they have the very good splitting pattern at the bottom, the A is the one which is having having without any host molecule, and the B is the one is the when you increase the guest molecule, it will keep on getting complex. Okay, so that the location of methane has been shifted from 3.1 to 2.5. Okay, it's been relocated. I can say it's a relocated. Okay, it's because it's experiencing the shielding effect of the host molecule. The host molecule is basically shielding the magnetic force of the external magnet. So the methane molecule of that one, having the hydrogen, that nuclei, the nuclear spin, okay, and the radiation could be controlled by the host system. Okay, that is why it is having the shifted from the 3.1 ppm to like 2.5 ppm. So this is the beauty of supramolecular chemistry. So you can understand it cannot accommodate more than one molecule into the host molecule. Okay, and from that you can understand whether your compound is pure in nature. Suppose if it's not a pure, if your compound have a two kind of mixture, you can easily differentiate whether this is a single molecule or whether it is a combination of two molecules. Okay, so this is very easy to utilize in various fields. Okay, as I told you, still supramolecular chemistry has been not utilized fully by other field working those who are working in the other fields. So this is another example through which this is a kind of inorganic complex. Okay, this inorganic complex having the adamantine amine, so that is the R group, and this is a ruthenium complex. Okay, so even this is the inorganic complex, it can accommodate the part of the molecule. See, for example, adamantine amine can be accommodated inside the cavity. So only adamantine amine can penetrate inside the cavity, whereas the rest of the part will stay outside the cavity. Okay, so we can check the NMR, and this is the NMR. But here you can see that it's wonderfully the host peaks. See here the host peak. This is the even though this is a molecule, cucurbityrol is made by the it's a small polymer made by the glycosyl, and these peaks basically having the hydrogen peaks of the glycosyl, which appears between the the A++ and B+. Okay, and C is the one which basically is come from another hydrogen source. Okay, so these doublet and this singlet and the doublet, this is what you will get from the cucurbityrol as a host molecule. Even the host is a big size and they are symmetrical in nature, and because of the symmetrical in nature, you may expect only a similarity peak between the kind of peaks, like located at I think this 5.5 and this around 4.1, and there's one peak around 5.2. Okay, so this is the peak usually we get for the cucurbityrol. As I mentioned, because of the symmetry, all the hydrogen ions, all the hydrogen nuclei, they're located at a particular peak value. Okay, so when they experience, for example, part of the hydrogen, when they experience in a different environment, because of the guest inclusion, they give a shift. Okay, that is why there is a shift in this nature of the host molecule. Okay, so when there is a shift, we can understand there is a complexation has taken place. Okay, so this complexation phenomena, okay, will easy to help us to understand about the nature of the molecule. As I mentioned to you, even you can understand whether the molecule is a single molecule or whether there is a variation within the molecule itself, we can understand that. Okay, if there is a within the molecule, if there is a variation, suppose like you have adamantine amine, instead of adamantine amine, suppose adamantine amine is impure, for example, if it has some methyl substitution somewhere, okay, that particular methyl substitution may be difficult to detect by the simple NMR, but that can be detected by the complexation. After the complexation, surely instead of double doublet, here as you see here, this doublet has been shifted to two doublet, And the second thing is that upon complexation, this doublet sharpness also vanish. So it will be more broad. That also will indicate how they are interacting. Okay. So during the interaction process, the molecular weight, the molecular number being basically increased. They behave as a single molecule. That's why, the broadness comes as the molecular weight increases. Okay. And the solubility also drastically differs. So this is the, pictorial representation to show that how the host, when there is no guest molecule, how the NMR looks like. When there is a host-guest complex, how they change. Okay. And this is what the difference is. And here in between 4.8, there is also a water molecule. There is also water peaks are there. Okay. So even though you're using D2O, but there could be a small amount of H2O will be there. That usually appears in 4.8. Okay. Here we have removed that peak to show that how the chemical shift could be easily understandable. Okay. So this is how the guest molecule, the behavior of the guest molecule can be studied by the host molecule. So CV7 is basically it's a water soluble. That's a big advantage. So this can be even if you take a small pinch of the CV7, for example, you require only 2 milligram or 3 milligram of the host molecule. That's good enough to measure the NMR. Okay, and put your guest molecule, and you can easily understand whether your molecule can be inside the cavity or not. Okay, so if it's inside the cavity, as is shown here, earlier case, there will be a chemical shift. For example, as we see here, the beta and the methyl part of the amine. So see here the chemical shift. It is from 4.02, it is moving up to 3.5. So the total overall plus or minus, whatever may be, it is going to be around 0.5. Whereas in the case of CH3, it is moving 3.1 to 2. Around 2.1. It's a 1 ppm range difference. So that indicates the amine part is totally inside the host molecule. That is why the shielding effect is very high. Okay, that shielding effect tells us that how strong the ammonium moiety has been interacted with the host molecule. Okay, so this is how you can find out whether your molecule having any good interaction with the host molecule or not. You can easily understand. And what is the advantage of host-guest complex? You may think about that. Why should I make a complex? What is the advantage of this one? See, there are so much advantages. For example, very simple example I can tell you that cisplatin is a complex. Cisplatin is an inorganic complex. Basically, this complex has been given for as an anti-cancer agent, effective anti-cancer drug molecule, which is available in the market. Okay, and this cisplatin can be also having a lot of toxicity. When you take the chemotherapy, you know that how difficult the patient to survive in by the drug molecule. They will lose the hair, they will lose the abdomen pain will be there, and they will lose the appetite. So a lot of difficulties they will come across. To avoid that one, when you complex the cisplatin inside the host molecule, for example, cyclodextrin or even cucurbitacin, the entire toxicity been totally removed. Okay, and of course, the activity of the anti-cancer activity also a little bit reduced. But at the same time, we can avoid the toxicity of the drug molecule. That's one simple example. I want to tell you that why the host-guest chemistry and supramolecular chemistry steadily getting attention into the scientific field. Okay, because of it can block whatever be the negativity of the particular drug by simply make it complex. Complexation is you don't need to do anything. You don't need to heat it. You don't need to do anything. Simply mix together, you will get a wonderful complex. Okay, that is how we can understand the host-guest system by the NMR. For that only, I'm giving the example of this one. And after the host-guest complexation, you can separate the guest and the host. As I mentioned to you, your guest is mostly organic soluble, whereas your host is other organic soluble. So you can easily separate the uncomplexed material. And then you can just simply submit for any kind of activity, biological activity, you can submit that. Okay. Through that, you can easily publish a paper, patent, or whatever that. Okay. So that is the beginning of the supramolecular chemistry in real applications. So for example, here, this is the example, pseudorotoxin. We call this a pseudorotoxin. And usually, whenever there is a organic moiety, whether it is attached to the polymer, whether it is attached to the gold nanoparticle, or whatever be the source it has been attached, but still material can make a complex with a particular molecule very easily. Okay, so when after complexation, we call it the protoxin. Okay, and NMR of this also helps us to understand how it has been complex. As you see here that through the 2D NMR, we could able to characterize very well that it has been complex. The simple CB7 NMR is given here, whereas after complexation, you can see that how the chemical shift has been occurred from that to this one. Okay, so even though whether this is attached to the polymer or whether attached to the nanoparticle or whether it is a free in state, so whatever be the condition, the host can easily penetrate and they can make a complexation very easily. So this is another example I want to show you that. I don't know how many of you know about this molecule. This is called a Taxol. Taxol is another big, big advantage happen in the medicinal field. After the discovery of a Taxol, many of the cancer patient has been survived because this wonderful molecule can help to solve the cancer disease. Okay, so that is why this Taxol gain much attention into the scientific field. And as you see here, how complex this one is. The molecule itself is very complex. That is why until now, no good synthetic method is available. We cannot make it. We cannot make it this molecule by synthetically. Then how it's been available in the market? So this has been extracted from the plant only. There's no other way. And there are some companies they are making by the by genetically modification of the plants. Okay, and then they are producing this Taxol. So when I was in Korea, we usually get the Taxol drug molecule through a company which is basically generating the Taxol through genetically modified plant. Okay, so like that. But what is the chemistry? What supramolecular chemistry can I do with this one? This molecule also can be complex with a CB7. So this is the NMR of the Taxol molecule. And as you see here, they are so complex. Okay, there are so many peaks, but still a good NMR specialist can identify which proton comes from which part of the molecule. That is the beauty of the NMR chemist. So in our lab also, we had one NMR chemist who could able to solve any kind of NMR problem. Okay, he will easily just run 2D NMR. He will understand and he will tell us from the NOSI, from the COSI, he will understand and he will tell us, okay, this is the structure of the molecule. So that is how they're finding the even very complex molecule. We can find out the structure of the particular molecule. So this is the proton NMR. We got it with a CB7. So this has been patented. Okay, we filed a patent for this one in Korea and as well as in other countries. And basically, still we have not explored what kind of application of this complex, but we just understood that how CB7, after we adhere the CB7 to the polymer, we could able to separate some of the this Taxol from the natural product. That's what we demonstrated here. So that helps us to identify and to separate the natural product. So CB7, cucurbitol or the other host molecule, you can just use as a clip to catch the molecule and then it will trap the molecule very specifically. The molecule which can be complex by the host molecule. That alone can be captured. Because suppose you have a cooker material, okay, or if you have cyclodextrin, if you can attach the host molecule into a polymer. Polymer means it's a kind of bead, right? Like a silica gel. So you can pack in the column, okay, and then you can just run the natural product. Then only a specific molecule which is having the bioactivity can be trapped, and then later on, by changing the polarity, you can remove the bound molecule, and you can extract one single molecule from the so much complex molecule. So that is how supramolecular chemistry and the NMR is going to help us. Okay, and this is another example which I want to show you that what will happen if there is no complexation. That is the question, right? Naturally. So everyone want to know what will be the NMR when it's complex, then what will be the NMR when it is not complex. Okay, if it is not or fully complex, usually the broad peaks will appear. As you see here, the A is the one which represents the pure organic molecule, and when there is no complexation, usually they appear very broad in nature. Okay, this is how we can see that. Okay, that means there is no complexation at all. So another thing is that this also can help us to understand the dynamic nature. This is what we call molecular machine. Recently, Fraser Studart, who got the Nobel Prize for making the molecular machines. Okay, so these molecular machines also can be monitored by the cooker material or by the host molecule. Okay, so what is meant by molecular machine? So molecular machines are nothing but they are the one which have the freedom to move. Okay, I will quickly finish it up. Okay, I'll show some examples and I'll quickly finish it up. Okay, so this is the molecular machine. As you see here, they can rotate and they can move. This like a wheel, and this is the kind of a spindle. Okay, so in the rod, the host molecule can locate it in a different location depending on the pH, depending on the solvent, depending on the the attractive force between the molecular location. So we call molecular station. So molecular station 1, molecular station 2, molecular station 3, like that. Okay, so I'll give an example from the NMR how we can detect that. Okay, so this is the molecule as you see here, the bottom one, and this is the one. See, when the CV8 is located at a different location, then usually the peaks of D and E, okay, they are basically move in a different location. The chemical shift, change the chemical shift. It undergoes different chemical shift. But at the same time, as you see here, when there is a CV8 basically located in a center of the molecule, there's a station 1. Okay, so when they are located in the station 1 and the station 2, so both are having a different chemical shift value. Okay, so as you see here, the chemical shift value totally changed of the host of the guest molecule. So the host molecule peaks are staying as it is. As we see here, doublet and then another doublet, singlet. This is the, as I told you, very easy to detect whether CV is there or not. But upon complexation, as you see here, the CV8 peak also having a variation. They also shift. Why they shift? Because as I told you, part of the hydrogen molecule also experience a similar kind of a location. Okay, so depending on how they, the shielding effect varies by the complexation. So this is another example to show you the same thing. So depend on the complexation. If this is the case, complex like a 2 to 3 system, and this is the complex system like a 1 to 2 system. Okay, so all these cases, the chemical shift will guide us. Okay, what kind of a complexation it has occurred. Okay, so that is the one simple example. Now I will go to the medicinal field. Okay, so for example, so MRI. So MRI is nothing but is another application of NMR only. Okay. So we can also scan our body, brain, and various organs. We can scan by the MRI. Okay. So usually they use the xenon 129 for that purpose. Okay. But now they understood that CV7 can easily accommodate the xenon molecule. As I told you, it's very difficult to say which molecule will be accommodated by the host molecule. It's very hard to predict. That is why so many publication has come with a Hooker material. It can accommodate even like a noble gas, okay, such as xenon. It may be a great wonder, okay. And this is basically under the host molecule, and we'll see the NMR pattern of that one, okay. So when the xenon is inside the CV7, so when it's inside, they located the different ppm. When there is the outside, so we call the xenon in, xenon out. So both having a different spectrum. Whereas when you are having only simple xenon, we get a different kind of a spectrum. Okay. So that tells us how this host molecule will help us to even further in the future of MRI. Okay. So suppose if you have a disease, for example, that having active with acetylcholine, for example. So acetylcholine, it's a kind of neurotransmitter. So if the neurotransmitter plays a role in the disease, then what will happen? The xenon will be replaced by the acetylcholine. Okay, naturally you can understand, the location of the particular xenon will be totally different. So through that, we can even understand in the molecular level, the early stage itself, we can detect the kind of cancer. So those kind of applications, I'm sure at some point, surely will occur. Okay. So this cucurbitol is going to contribute even for the detection, early detection of cancer. Surely at some point it will appear because there are many people are working on this field. Okay. So this is the kind of, xenon 130, 129 NMR. So we can see the, as you see here, we can easily do the scanning of the organ. Live organ, you can easily scan that. So next to the NMR application is that, it also helps to find out the binding constant of a host system. I think this is very routine and, the job lot is the one which everyone, those who are working in the host system knows about this one. So I'll skip this one. So this is the one like by the addition of a different concentration of the guest molecule. Usually the chemical shift also varies slowly. So that we can plot, okay, by plot and then we can get the binding constant value. This is a very routine process. Those who are working in the host system, they do very regularly. And this also helps to, NMR also helps to understand the reaction kinetics. Okay. I think many of the organic chemists, they are utilizing the NMR to study the reaction kinetics of the particular reaction. So this is also very, one of the wonderful applications of the NMR. So again, like, this is the fluorine molecule. It's a so big molecule, right? It's a fluorine is a kind of a, we call it a bulky capsule. Okay. And this also having applications in the solar cell and so many applications are coming out these days. Okay. And this such a bulky molecule also can be encapsulated by the host molecule. Even CV7, we published one paper that C60 can be encapsulated by the CV7. So another big thing is that NMR also help us to understand the protein folding. So the protein folding is also a huge application in the medicinal field. So to understand, the disease-oriented, protein, we monitor those proteins. Some of the memories of even Alzheimer's disease is based on the folding of the protein. Okay. So this protein folding can be easily monitored by the NMR. Of course, this is also in the infancy state. So it's hard to just only, outside the biological system, we can measure all these things. But inside the biological system, it's hard to understand this folding and unfolding of the protein. But in the future, probably by the technology development of the NMR, we could able to to monitor several of the disoriented proteins. So this is a simple example to show you that when there's a folded, what kind of NMR we get for a protein, and when there's unfolded, what kind of NMR peak we get out of this one. Okay, so that indicates that how NMR can be helpful for understanding the folding and unfolding of the protein molecule also. And even you can do the 2D NMR to understand even deeper level. So nowadays there is also coming a new field we call NMR crystallography. So usually the crystallography can be done with the help of XRD only, but these days NMR is also helping to understand how the crystalline nature can be identified by the NMR. Okay, so this is a simple example. I want to show you that how the XRD spectrum can have some connectivity with the NMR. Okay, so this is the top one is the unit cell XRD pattern, and with that one of that they are also comparing with the NMR unit cell content. And slowly, I think, as I told you, it's still in the infancy state, but at some point probably using the NMR we can also find out the structure of the molecule in a more precise level in combination with the XRD. So this is another example which I want to show you that even the polymer, this is a kind of supramolecular polymer made by the cooker material. This is what we call as molecular capsules. Okay, and this molecular capsule has the advantages that the capsule can be decorated by any kind of test molecule. For example, folic acid is the one which basically represented in the cancer cells. So that capsule can be decorated by the folate, so that you can specifically goes to the cancer cell, and inside the cavity, inside the capsule, we can load the drug molecule, specific drug molecule of the cancer, so that you can deliver only to the cancer cells, not to the normal cells. Okay, those kind of research line is very much going on. Okay, it's also very fancy chemistry. Okay, and how the NMR is going to help, that's what we are going to see that. Okay, so this is the one solid state NMR. Okay, so solid state NMR through which we can understand whether that is monomer stage or whether this is in the polymer stage. So all those things also we can study by the solid state NMR. So here we have done the solid state NMR to understand there's a polymerization occurred, and to using the SEM we proved that the molecular capsule has occurred, and through the TEM also we proved that the thickness of the capsule. Okay, so there are various techniques like solid state NMR or a particular nuclei NMR like fluorescence, like fluorine NMR or xenon NMR. So through that different elements of NMR also we can understand more deeper level of the molecular level. Okay, almost I'm going to the close of my talk. So NMR in basically it can be applied in various fields. It can be for use of molecular imaging, metabolic profiling, molecular structure and dynamics, and molecular interaction, and for drug delivery, and of course for the agriculture and food industries, polymer and solid materials, paint, and everywhere it is used. Even the most presently we are using for the chemical synthesis and the reaction monitoring, we are using the NMR. So NMR can be applied in food and membrane to study all sort of things. Okay, and with that I would conclude because as time is pushing me. Okay, I'm thankful for you for your patience. So the first statement I said the electron spin, I forgot. There's a nuclear spin. Okay, so the nuclear spin is the one responsible for the NMR. Okay, not the electron spin. So how the nuclei, like how the hydrogen nuclei, how the carbon nuclei, and how they are spinning, and how they are acting as magnets. Okay, and through the magnetic interaction, how we are getting basically the NMR. Okay, all about the spin of the nuclei, not the spin of the electron. This is I want to correct it. With that, I would conclude my talk, and I would be happy if you ask any questions. Thank you very much, sir.
Thank you, sir. Thank you, sir, for guiding us. And this information will be definitely very, very useful to us. That is the time to move towards the question answer session. And in the chat box, there is only one question from Ajay Thakur. Sir, do you teach supramolecular chemistry? If yes, which book you use to teach UG students?
I'm sorry, madam.
Sir, Ajay Thakur is asking which book you are using to teach UG students
UG students usually not from this kind of.
for supramolecular chemistry.
Madam, this is only introduced to the PG level students, supramolecular chemistry until now.
Okay, okay, sir.
Because this is very difficult to understand, the host and the guest kind of system. And particularly, the reaction dynamics and the binding constant studies are very difficult to understand in the UG level.
So for that, which book you used
Which
for teaching?
Which group, madam?
Which books? Or
Which
names of-
book?
Yes.
I say. So there are so many books, madam. It's even my own Professor Kimun Kim has published one paper on cucurbitacin.
Okay.
I'm the co-author of the book.
Okay, thank you, sir.
Yes, madam. Thank you, ma'am. I would like to thank Professor Swaminathan for the invitation, and also I would like to thank the organizer Gurnule, who has contacted me frequently, and thank you, Madam Rashmee Dubey, for the nice introduction and also to taking care of the sessions. I thank all the research scholars and the faculties, madam.
Here is one
Thank you.
question also. Here
Yes,
is one
madam.
question. If a supramolecule is insoluble in solvent, how can we take help of NMR? Whether solid 13 carbon works there?
Yes, madam. Basically, as I mentioned to you, you can use the carbon 13, but I think proton NMR is good enough to understand the chemical shift, because in the case of carbon 13, chemical shift cannot be observed.
Okay. Sir, one question from Dr. Mahna Malviya. She is facing problem with the CB6 solubility. How can resolve this problem? She is asking how to resolve the problem.
Yes, madam.
of
CB6 can be easily soluble in water by adding small amount of sodium chloride. If they add a pinch of sodium chloride, is good enough.
Yes, sir. Thank you, sir.
Yes, madam.
I just want to ask Dr. Gurnule.
Yes, madam.
Yes, sir. Because when, as you have explained very nicely about the biomedical applications and encapsulation and all that. So if the drug is having solubility in different solvents, so how you can just going for the extraction CB?
Yes, madam. For example, if they complex in the water, for example, even though it's a soluble in organic solvent.
Yes.
Even though if there is no solubility in water at all, that's not matter.
Yeah.
But when
So
you
are
mix,
directly adding the drug to the solution of CB?
yes, exactly.
Okay. Thank you.
Okay, thank you, sir. Thank you, all of you.
May I ask a question?
Yes, madam.
Yes, ma'am, please.
Good afternoon, sir. Very nice lecture, sir. Actually, this is the first time that I'm learning about host gas chemistry, research on host gas chemistry. Otherwise, I was from adsorption side. So, yes, we are facing the problem. Actually, I'm an AP in Bhilai Mahila Mahavidyalaya. But the fact is, when we interpret the NMR spectrum, you were very right in saying that the softwares we use are correctly are just giving an intuition on what the functional groups or what the spectrum is showing. But students of my group, I can say, we are not getting the proper guidance, because the place where we are going to analyze our samples, the technician can only give us through the software. We are not getting some particular person or particular expert who can guide us how to do and what to do. Okay, from the books we can learn the way, but the exact representation is quite difficult, sir. So can we form a forum in which scientists like you can guide us, a forum where any sort of problems which the research scholars face or the young teachers face can be solved in such a forum, where XRD or FTIR or any analysis of this kind, NMR spectrum, can be easily sorted out? This is only a suggestion, sir. Can you make this out, sir?
Yes, but ACT surely should do that, because this
Yes,
is a chemistry teacher association.
Fine,
I request the AC to make a forum for this.
Sure, sir. It will be so helpful for us. We'll tend to learn, sir. We want to learn, and we are not getting a particular platform. Means we need some platform where the senior teachers can guide the younger teachers, and then this will be following up
Yes,
gradually.
actually, you are rightly said, because India is so scattered. This is what
Yes, sir.
exactly ACT should play a role.
Very true, sir. I'm very thankful that I could hear your lecture. So I'll be liking to have in touch with you through email, so that I can further ask any queries if I have. And I would like to go for the host guest chemistry research also. It's so nice to know from you the beginnings and the frontiers part. Thank you so much, sir.
Yes,
I'm
madam.
overwhelmed. Thank you so much, sir.
Thank you, madam.
Thank you. Thank you all. Now, I hand over the session to Dr. W.B. Gurnule, convener of this national webinar. Over to you, Gurnule, sir.
Thank you, madam. Today's ACT National Webinar on Instrumental Methods of Analysis was organized by the Association of Chemistry Teachers in association with Department of Chemistry, Kamla Nehru Mahavidyalaya, Nagpur, and Kala Salingam Academy of Research and Education, Krishna Koli, Tamil Nadu. This has been very nice of all the guests to come over here and enhance the grace of this webinar. First, I would like to thank respected Dr. Vanjari Madam, President of Amar Seva Mandal. They always have been a source of inspiration for us for organization of such type of webinars. As a convener of this webinar, I am thankful to Honorable Advocate Abhijit Vanjari, Secretary of Amar Seva Mandal, for their kind support in organizing the webinar. I also express my thanks to our chief guest, Dr. Smita Vanjari Madam, Treasurer of Amar Seva Mandal, who accepted our invitation and delivered a graceful speech in the inauguration session. First, now again here, I would like to thank respected Professor Damodar PrAbhu, General Secretary of ACT. They always have been a source of inspiration for us and for giving an inaugural address in the webinar. As a convener of this national webinar, I am thankful to Professor Brijesh Pare, the President of ACT, for their kind support in organizing the webinar and accepting our invitation to preside over this national webinar. I express my thanks to our national convener of ACT Research Convention and the Secretary of ACT Central Zone, Professor Rakhi Gupta Madam, who accepted our invitation and delivered a graceful speech on this occasion about the research convention. I am personally and on behalf of organizing committee thankful to resource person, Honorable Dr. B. Sridhar, who delivered a talk on the surface characterization by X-ray photoelectron spectroscopy. I am also thankful to Professor Uma Sharma Madam, who delivered a talk on the Mosba spectroscopy for acknowledgeable talks delivered here. I also thanks to the invited speaker, Professor PUNDLIK Bhagat, sir, for their excellent talk delivered here on the topic optimum use of instrumentation resources to maximize the research output. I also thanks the invited speaker, Professor N. Selvapalam from Kalisamana University for their excellent talk delivered here on the topic application of NMR in supramolecular chemistry. I also express my thanks to our principal, Dr. D.S. Badwaik sir, Dr. P.B. Daikar sir, Vice Principal, and faculty members of Kamlanir Mahavidyalaya for cooperation from time to time to make this webinar a grand success. I am grateful to the officials of Kalasalingam Academy of Research and Education, Krishnakoli, and particularly I am thanks to the Professor M. Swaminathan sir. I express my thanks to the Executive Council officials of SCT and members of SCT for their support in organization of this national webinar. I am also thankful to all the participants for giving a warm response to the webinar. At last, I give here thanks to all those who have helped us directly or indirectly to make this webinar a grand success. So here one announcement is there. Feedback form will be shared in a chat box. So participant kindly fill that. Thank you.
Thank you.
यहाँ पे पार्टिसिपेंट